I am Pushpanjali Pandey. I am going to take a class on role of energy efficient sinusoidal PWM waveform generator in digital signal processing. The topics overview, introduction, related work, energy efficiency, thermal analysis, conclusion, the future scope. Overview. This is an approach to design energy efficient sinusoidal PWM waveform generator on FPGA that not only consumes low, low amount of power but also providing more security. PWM is used for encoding. Hacker dreams to hack the encoding process and use it for their one malicious introduction. Overview. Our proposed FPGA based PWM waveform generator in is more secure as hacking of hardware based encoding by PWM waveform generator is, is almost impossible to break. There is a reduction of leakage power in the percentage of 16.86 percentage, 52.17 percentage, 39.13 percentage, and 21.73 percentage. We we scaled down ambient temperature from 50 degrees Celsius to 0 degrees Celsius, 12.5 degrees Celsius, 25 degrees Celsius, 37 degrees Celsius, respectively. Introduction. We have analyzed the various varying power with the different level of temperature in order to develop the energy efficient sinusoidal PWM waveform generator. The whole process of hardware based design make it very tough to break into for any expert cyber hacker that leads used to develop a more secure PWM waveform generator. In this work, we have used four different clock frequency 15 MHz, 71.42 MHz, 125 MHz, and 500 MHz. And we have used four different wave pulse frequency 33.33 MHz, 47.61 MHz, 83.33 33 megahertz and 333 megahertz, 33 point megahertz, respectively, for the different level of ambient temperature level. Introduction: Spartan 6 FPGA family is used for simulation and amount of total proofs consumed is noted down. Spartan 6 family is used, which has greatest system in integration ability to produce outcome. Spartan 6 family is used, which has greatest system intro integration ability to produce outcome. Some characteristics uh, features about Spartan 6 are shown, shown in figure 1. Some important features about Spartan 6. Spartan 6 FPGA features FPGA 1 Gilix Spartan 6 three types of slice energy. Every CLB has two slices. Low power dissipation, efficient LUT logic. FPGA used in our research. FPGA Spartan 6 process technology 45 nanometer. Block diagram of the Gilix Spartan 6 model. RTL symmetric. RTL is acronym for register transfer level. This block diagram differentiates the external architecture of the M3 model, which has total 4 ports on each clock input port and other 3 are output port, which given the PWM waveform. Features of PWM generator. Features of PWM generator. Pulse width modulation, precision control, variable frequency, duty cycle, constant current, constant voltage, dead time, diode, diode, transistor, synchronization, output stage, MOSFET, MOSFET, IGBT, BJT, protection over temperature, over current, short circuits. Components of implemented design. Table 1. Components of implemented design. State. Encoding. Adders. Register. Adders 3. Register 5. Comparator 1. Finite state machine 1. Related work. In one of masterpiece of researchers have made energy efficient ALU using mobile DDR IO standards. One. In our work, we are making energy efficient PWM in place of ALU. We are using thermal slice and frequency scaling in place of mobile DDR IO standards. Related work. Some well-known re- researchers have also dig- di- designed an energy efficient multiplier using Nikhilum Northam's Northam's theorem, the Vedic technique. In our work, we are making energy efficient PWM in place of multiplier. We are using thermal scaling and frequency scaling in place of Nikhilam Nautam's Charam Dastak Vedic technique. Related work in another research has done power dissipation analysis of DES algorithm implemented on 28 nanometer FPGA. Some research have used thermal away approach in encoder in design and also technique. Thermal stably by working on different ambient the temperature. We are also using thermal and frequency scaling for the making of design of energy efficient sinusoidal PWM waveform generator. Related work. Some other res- research have made energy efficient thermal aware image ALU design on FPGA. On researcher tried to analyze the energy of optimization possibility in counter design by selection of energy efficient IO standards. We are making a design of energy efficient PWM waveform generator. We are using different level of thermal scaling and frequency scaling in place of IO standard. Related work. Some research work have made thermal efficient ALU design by use six different members of SST IO standard. We are making energy efficient PWM for ALU. For the work we are using thermal and frequency scaling at different level of ambient temperature and frequency. Research have done power and analysis of DES algorithm implemented on 28 nanometer FPGA use HTML H4HSUL T4TTL M4 mobile DDR L4 LVCMOS technology. We are using thermal and frequency scaling instead of HTML. Result: there is a fall of 20 to 61 percentage in the leakage power as the ambient temperature is scaled down from 323.15 Kelvin to 273.15 Kelvin, 285.25 Kelvin, 298.65 Kelvin, 310.65 Kelvin, respectively, and the total power goes down by a percentage of 60 by 47 percentage as the temperature level is scaled down done from 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin, respectively, as can be vividly concluded from table 2. There is no changing. There is no change in dynamic power watt on when room temperature is decreasing from 300 to 23.15 Kelvin to 273 point 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin. Result table 2. Power dissipation when clock period is 50 megahertz and period of wave plus is So, pulse is 33 per room temperature in Kelvin. 273.15 Kelvin. Dynamic power 0.010 watt. Static power 0.009 watt. Total power 0.00919 watt. Room temperature 285 degree 85.65 Kelvin. Dynamic power 0.010 watt. Static power 0.011 watt. Total power 0.021 watt. Room temperature 298.65 Kelvin. Dynamic power 0.015 watt. 0.010 watt. Static power 0.014 watt. Total power 0.024 watt. Room temperature 310 point 310.65 Kelvin. Dynamic power 0.010 watt. Static power 0.0118 watt. Total power 0.028 watt. Room temperature 323.15 Kelvin. Dynamic power 0.010 watt. Static power 0.023 watt. Total power 0.033 watt. Result: there is a fall of 21 to 61% in the leakage power as the ambient temperature is scaled down from 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin respectively, and the total power goes low by a percentage of 50 to 43% as the temperature level is scaled down from 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin respectively, as can be vividly concluded from table 3. There is no changing in dynamic power what, what which is constant when room temperature is decreasing from 300 to 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin. Result: table 3. Power dissipation when clock period is 71.42 megahertz and period of wave plus is room temperature in Kelvin 273.15 Kelvin. Dynamic power 0.007 watt. Static power 0.009 watt. Total power 0.016 watt. Room temperature 285.65 Kelvin. Dynamic power 0.007. Static power 0.011 watt. Total power 0.018 watt. Room temperature 298.65 Kelvin. Dynamic power 0.007 watt. Static power 0.014 watt. Total power 0.021 watt. Room temperature 300, 310.65 Kelvin. Dynamic power 0.007 watt. Static power 0.018 watt. Total power 0.025 watt. Room temperature 323.15 Kelvin. Dynamic power 0.007 watt. Static power 0.023 watt. Total power 0.0330 watt. Result: there is a fall in the total power goes low by a percentage of 12 to 35 percentage as the room temperature level is scaled down from 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin respectively, as can be vividly concluded from table 4. There is no change in dynamic power watt when ambient temperature is decreasing decreasing from 323.15 Kelvin to 273.15 Kelvin, 285.65 Kelvin, 298.65 Kelvin. Result: Table 4. Power dissipation when clock period is 125 megahertz and period of wave pulse is room temperature in watt in Kelvin 273.15 Kelvin, dynamic power 0.017 watt, static power 0.009 watt, total power 0.026 watt, room temperature 285.65 Kelvin, dynamic power 0.017 watt, static power 0.011 watt, total power 0.028 watt. Room temperature 298.65 Kelvin, dynamic power 0.017 watt, static power 0.014 watt, total power 0.031 watt. Room temperature 310.65 Kelvin, dynamic power 0.017 watt, static power 0.018 watt, total power 0.035 watt. Room temperature 323.15 Kelvin, dynamic power 0.017 watt, dynamic power 0.023 watt, total power 0.040 watt. Conclusion: dissipation in terms of dynamic power, leakage power, and total power are observed. It's, it is it is quite obvious from power dissipation that at high, higher values of ambient temperature, more leakage power is consumed and vice versa. There is help in this diagram. There will help in designing low power sinusoidal PWM waveform generator for efficient output. Conclusion: Spartan 6 takes less energy. That's why it is efficient for not only sinusoidal PWM waveform generator design but also for various in electronic design. The frequency range from from 15 megahertz to 500 megahertz for clock pulse and 33.33 megahertz to 300 333.33 megahertz for wave pulse. Conclusion: for this frequency range, the values of clock and IO standard IO power remains sum and logic and signal power is neg- negligible for different level of changing the ambient temperature, but due to leakage there is noticeable difference in total power consumed. Work is done in order to have heavy and efficient design. Hardware based design is very hard to break by hacker. So this design design has a potential to develop security. Future scope. We may applied encryption algorithmic for encoding during making efficient sinusoidal PWM waveform generator on FPGA. The work has been done on one various frequency at different level of ambient ambient temperature. It is important to make the useful device device efficient, and a lot of work can be done in this further further future scope. We can also use different FPGA family like automotive, RTX 7, automotive, full runner 2, Kintex 7, automotive, Spartan automotive, Spartan 3A, DSP, Spartan 6, automotive, Spartan 3A, S, SOC, automotive, Spartan 3E, 3D, IC, automotive, Spartan 6, ultra, scale, architecture, Spartan 3, and Spartan 3E. It is important to make this useful device efficient, and a lot of scope is open in function enhancement of our proposed design. Reference, 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 reference. Thank you. Mail me your question on pushpanjali.pandey@gyancity.com.